Describing a relation using different ways. Wow, awkward or what? How about different ways to describe a relation? A relation can be described using words, a table of values, a set of ordered pairs, an arrow diagram, a graph, label the axes, plural, or an equation. It cannot be described using domain and range. Remember yesterday we did domain and range. You can't describe a relation that way, but that is certainly part of the information. Okay, situation 1. A plane begins to land at Calgary Airport from an altitude of 8,000 meters at a rate of 1,000 meters per minute. So at a time of 0, we are at 8,000. 1 minute later, we will be 1,000 meters lower. And then we'll drop to 6,000, 5, 4, 3,000, 2,000. 1,000 and 0. Writing these as ordered pairs, as a set of ordered pairs, we need a brace bracket. And remember that the height depends on the time, or the altitude depends on the time. What? Erase. 5, 3,000. 6, 2,000. And remember, ordered pairs are enclosed in parentheses. 7, 1,000. And lastly, 8 minutes, an altitude of 0. And close off the set. Equation using appropriate variables. So, what would an appropriate variable be? This could be t for time and a for altitude. So the equation, well, a is equal to, so what's happening? We're starting with 8,000 and then we're subtracting. So 8,000 minus 1,000 t. So when t is 0, this will be 8,000. When t is 1, it's 8,000 minus 1,000, which is 7,000. When t is 5, it's 8,000 minus 5,000, which is 3,000. So this works, right? We have our variables, and we have an appropriate equation. We can graph this. So this is time, our independent, time in minutes. So if we're using time as a variable, we have to define, is that minutes or seconds? And I need to turn kind of sideways-ish here so that I can write altitude in meters. It's really weird writing on a tablet this way. Okay, so at time 0, these are our ordered pairs, right? So 1, 7, 2, 3, 4, 5, 6, 7, 8. Is the data discrete or continuous? Is there an altitude for 30 seconds or 1 minute and a half? And you say, yeah, certainly there is. The plane is going to descend through all values of altitude from 8,000. I'm actually amazed I got that straight of a line. from 8,000 meters down to 0 meters. So it is continuous data. The altitude can be worked out for any time t less than or equal to 8. Right? So for any value of time less than or equal to 8, we can get an altitude. Situation 2, complete the table by stating the degree of each polynomial. So the degree is the term of highest degree, so degree 2. This is of degree 4, and 1 and 0, so degree 4. This is of degree 3 and degree 2. This is of degree 4, degree 2, degree 0, degree 2, degree 1. Represent this relation with the following arrow diagrams. So polynomial and then has degree. And then we're going to do it in reverse. So what have we got? 2x squared plus 5x minus 4 has degree. Now you notice the degrees are 2, 3, and 4. So all we need to list over here is 2, 3, 4. And here we're going to list each of the polynomials. 3x cubed y minus 4x plus 2, 5xy squared minus 2y squared, x squared y squared minus 2xy minus 8, 7ab minus 26a. Now we can go up here. Oops. So the degrees are 2, 4, 3, 4, 2. 2, 4, 3, 4, and 2. So this polynomial has a degree of 2. And notice now we have arrows. Each one of these only has one arrow coming from it, but each of these, or these, may have more than one arrow coming to it. And if we reverse this, so now our degrees are 2, 3, and 4, and our polynomials, 2x squared plus 5x minus 4, 3x cubed y minus 4x plus 2, 5xy squared minus 2, so 5xy squared minus 2y squared, x squared y squared minus 2xy minus 8 and 7ab minus 26a. So 2 is the degree of this one, and 2 is the degree of this one, and 3 is the degree of this one, and 4 is the degree of this one, and 4 is the degree of this one. Situation number 3. A relation is shown in the arrow diagram to the right. Write the relation as a set of ordered pairs. So let's start with our inputs. So it's a set. We have the ordered pair -3 goes with 8. -3, 8. 0 negative 1. 0, negative 1. 1, negative 1. 5, 3. And 7. Oh, wait a sec. So you notice the 7 has two arrows coming from it. So we have 7, negative 1. And we have 7, 8. 7, 8. Which, being an ordered pair, needs to be in brackets and parentheses and a bracket at the end to complete it, to finish it off. So you notice that each element of the domain is listed only once, even though there are two ordered pairs that have a 7. And each element of the range is listed only once, even though 3 of these ordered pairs have a negative 1. Complete the table of values. So negative 3, 0, 1, 5, 7, and 7 again. Negative 3, the output is 8, 0, negative 1, 1, negative 1, 5, the output is 3, 7, negative 8, 7, or sorry, negative 1, and 7, 8. State the domain and range. Well, the domain is just what's in here, right? It's all of the first coordinates, negative 3, 0, 1, 5, 7, and that only needs to be listed once. So negative 3, 0, 1, 5, 7. Does the order matter? No, but it's easier if we put it in numerical order from lowest to highest. If everybody does that, then when we're looking at it, we're all looking at the same thing. And the range, there are only 3 range values, negative 1, just trying to decide, do I get the eraser? Yes. Negative 1, 3, and 8. So you can see from domain and range, there is no way to construct this. We have no idea. We know that negative 3 goes with one of these. We don't know which one, or if it goes with all 3 of them. We have no way of knowing the 7 goes with the negative 1 and the 7 goes with the 8. There is no information here other than if we look at the set of ordered pairs that defines the relation, that we will see negative 3, 0, 1, 5, and 7 in the first place, and negative 1, 3, and 8 as all the only possible value for the second element of the ordered pair. Situation 4, a couple is planning a wedding. The banquet holds up to 180 guests. For the banquet, they will be charged an $800 for a base fee plus $20 per guest. Complete the table of values to the right. Put the headings in the appropriate column. So let's call this number of guests. And if we want a variable for that, how about a little n? And this will be total cost in dollars, and we'll go with a capital T for total cost. So if nobody shows up, we have to pay the base fee of $800. If 50 people show up, it's going to cost us $20 per guest, which will be $1,000 plus the base fee. If 100 people show up, then it will be $2,000 plus the base fee. If 150 people show up, it will be $3,000 plus the base fee, right? So 150 times 20, so $20 per guest, 150 guests is $300, plus the $800, which is the base fee, which probably pays for the cost of renting the hall and such, and setup and takedown and cleaning and everything involved with the hall itself, and then the $20 per guest is for the meal and whatever. So write an equation to represent the relation where t is the total cost. So the total cost is equal to $20 times the number of guests plus the base fee of $800. So 20n plus 800, or some people might write t as 800, the base fee plus $20 per guest. We can graph this, labeling the axle. That's funny. Axle. Axes. Choose an appropriate scale. Wow. Given that the hall will only hold up to 180 guests. So this is our, let's look back. What is our independent variable? Will be the number of guests, and we have to go as high as 180. So how many ticks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm thinking 20. 180 divided by 9 is 20. 80, 100, 120, 140, 160, and 180. Perfect. If there were 10 of these, I would still probably use 20. I wouldn't use 18. I mean, 18 is a rough number to work with. You have 18, 36, 54. Not a good number to work with. This is the number of guests. We're calling that little n, so this is the n-axis. Now, what will it cost for 180 guests? 180 times 20 is $3,600. It will be $4,400, so we need to go as high as that. So let's see what we can do here. We have 1, 2, 3, 4, 5, 6, 7, 8. Well, if we go $500 each, 8 times 500 is 4,000. We'll fall a little bit short. So if we go $500 each, we got 500, 1,000, 1,500, 2,000, 25, 3, 35, 4. No, that's not going to do it. $1,000 each. 1, 2, 3, 4. That's a little rough. So if we just say, you know what, maybe we won't fit the 180 on here, let's go by 500s. So we'll call that 0. 500, 1,000, 1,500. Okay, 2,000, 2,500, 3,000, 3,500, 4,000. We have a table up here we can put in, so 0, 800, 0, almost should have gone by 400s. 400, 800, 12, 16, 2,000, that wouldn't go very high though. Could have gone by 800s, but whatever. 0 is 800, 20 is 1,800, 40 was, oh, we don't have that, we have 50. 50 was 1,800. $50 is 1,800. 100 is 2,800. 150 is 3,800. And here we go, there's our points, and they lie on a straight line. We could fill in other points if we wanted. We, could get values for 20 and 60 and 80 and such, but we don't need them. Is the data discrete or continuous? It is discrete because we cannot have a half of a guest, right? You can't have fractions of a guest. However, having said that, I'm still likely, because these numbers are so close together, right? If we plotted every single point, if you zoomed in, you would see a lot of dots. But, we can use a line just on the understanding that we know that we shouldn't be using a line. But this is helpful for, we'd say, well, if there's 80, then it's going to be almost $2,500. If there's 60, it's going to be this, right? We can read in between. We need to graph this on your calculator using the same window. So let's go to the desktop, and we will pull up a calculator. Open this up, close that window. So we need the equation for this, right? And we're going to do the equation as y equals 20x plus 800. So turn on. So let's do our window first. We can have from 0 guests to 180 guests. Let's go by tens. We know that 0 will be well, actually 800 is the minimum cost, but I want to see 0. Let's go to 5,000. And if we go by 500, then we'll have 10 ticks. We go to y equals. We're going to put this in. So 20x plus 800. Hit graph. And there it is. There's our graph. This will be 800 here, and that's climbing up. We went as far as 180, so this will be the amount for 180. And we've got basically that window. I did extend this up just a little bit, and I did scale a titch differently, but pretty much the same window. Wesley was standing at the edge of a cliff 100 meters high and threw a rock off the cliff with an upward velocity of 8 meters per second. The equation that approximates the height of the rock with respect to the bottom of the cliff is given by this, where h is the height in meters and t is the time in seconds. Complete the table of values below using times. Okay, so what do we want? 0, 1, 0, 1, 2, 3, 4, 5. Good, we've got some room up here. So this is time, which is measured in seconds using the variable t. This is height in meters using the variable h. 0, 1, 2, 3, 4, 5. And I need 0, 1, 2, 3, 4, 5. I am going to cheat. I'm not cheating. I'm going to use the calculator to do this for me. And you're going to learn something if you're watching this. So I'm going to go second function memory. And I want number 4, which is clear all lists, because I'm going to do something in the lists. So I can now go to stat. And I go to edit. And in list 1, I'm going to put the times. So 0, enter, 1, enter, 2, enter, 3, enter, 4, enter, 5, enter. And here's the cheaty part. Well, not really cheaty. It's just showing you. So I can do the formula up here. If I go up to L2, I can type -5, second function, L1. In other words, take the value from L1 and square it, plus 8, second function, L1, plus 8 times the value from L1, plus 100. Now, when I hit enter, what it's going to do is it's going to take the value of L1, substitute into the formula, and fill in the number here, right? So the first one, when it's times 0, that 0, it'll just be 100. At time 1, and it's a good idea to check one of these, at least one, to make sure the value comes out. So here I expect to see 100. With 1, this will be -5 plus 8, which is 3 plus 100. So I expect to see 103. So I'm going to hit enter. We should see 100 and then 103. And we do. So 100, 103, 96. So that's the lazy man's way, right? 100, I think as soon as I hit this, 100, 103, 96, 100, 103, 96, 79, 52, and 15. Of course, you have your calculator in front of you. It's not going to disappear on you. So you might want to watch that again. And the other way, of course, is just to type it in, right? Just go -5 times 0 squared plus 8 times 0 plus 100, enter. Let me show you that too, I guess. So here, let's quit out of that. -5 times 0 squared plus 8 times 0 plus 100. Now you might say, why are you doing that? You know it's just 100. Well, if I hit second function enter, it'll bring that back down, and I can go along here and change the zeros to ones and hit enter. Get my 103. Go second function, enter. I'm just going to do one more, and I can change the ones to twos. So I'm just arrowing along. Change one to a 2 and hit enter. And there's my 96, and so on, right? Just keep going. So that's another way you can do this on the calculator, so you don't have to retype it each time. Okay, what's next? Draw the graph on the grid below, label and scale the axis appropriately. Okay, so we need time in seconds from 0 to 5, so 0, 1, 2, 3, 4, 5. Let's make that 6. Call that time in seconds. And this will be our t-axis for time. And we need to go as high as a little bit higher than 103. So what have we got to work with? 1, 2, 3, 4, 5, 6. So I'm thinking 20. Basically, I have 100 divided by 6, right? So let's, if we go 40, 60, 80, 100, 120. So really, okay, we had 103 divided by 6 means that each one could be 17, right? Now, there's no way you're putting 17s here, so you go up to the next, kind of rounder number, and we go like 20s. If it had been 22, I would have gone 25, 50, and so on. Okay, we can now plot these. So 0, 100, 1, 103, 0, 100, 1, 103. Now you gotta kind of eyeball this, right? 2, what do we got? 96, 79, 52. So 96, 79, 52, just a little bit over halfway, 15, halfway between halfway. So halfway is 10, and then halfway between that is 15. Is the data discrete or continuous? Well, do we have a height for these different times? And the answer is yes, we do. And I think you'll find a lot of the time that when you're talking time, this will be continuous data. Unless we were talking about the number of photocopies we're turning out per minute, right? Because photocopies are discrete things. It's actually a bit of a curve. So it's not the line of best fit. It's a curve of best fit. So continuous. There is a height. For every time, at least until we hit the ground. Hit, oops, the ground, at which point we stop counting the time because it will be a height of 0. Display the graph on your calculator with the same window as your graph above. Verify the information on your calculator with the information you entered in the tables for Part A. Write the calculator window below. So, display the graph on the calculator with the same window as your graph above. Okay, so our window goes from, this time I'll go the same. So 0 to 6 by 1s and 0 to 120 by 20s. I'm going to peek ahead. There's nothing to peek ahead at. So, all right, now you have two things going on here, right? I actually already have this data in, right, because of the way I entered. If you didn't, then you would do the whole stat edit thing. You'd put in 0, 1, 2, 3, 4, 5. You would enter these by hand instead of using the formula. And now what we want to do is we're going to graph them, and I'm going to show you how that works. So, what do? We're going to go to window, and we're going to say my time goes from 0 to 6 by 1 second increments. My minimum height is 0, because that's when it hits the ground. My maximum height is 120, and I'm going by 20s. So that's the window. How do we make the dots show? we go second function y equals. This takes us into a menu called stat plot. We're going to do plot 1, and we're going to turn the plot on. Just means hit enter so that it's on. It defaults to the type of plot we want. It says my x values are in list 1. Remember, this is L1, 0, 1, 2, 3, 4, 5. Those are the x's. L2 are the y values. This is the mark that it's going to show. When I hit graph, you can see all of the points, which should look a lot like this, and they do. And we're going to do a lot of fancy calculator stuff as we go through math to draw in the equation of the line, to figure it out, to use it to calculate at this time what is the height, and at this height what is the time. That's all the stuff we have to look forward to using our calculators when we model certain situations. So write the calculator window in this format. So 0 to 6 by 1s. So this is the minimum x value is 0, the maximum, the greatest is 6, and the scale is 1s. It's what we call an ordered triple, and it's in square brackets because it's for a calculator, not. So 0 to 120 by 20s. And there was nothing else, and we are done this, and it's homework time.